All right, so we're taking a look at a method called integration using U-Substitution. Let me get my document up here. Okay. So this method is a way of taking a complicated looking integrand and making it look a lot simpler using rules that you are familiar with. Rules that would allow you to be able to find an antiderivative quite quickly. So as an example, insert. Let's make sure the pen works. Draw. Smiley face. Okay, so we've got using the method of U-substitution. So this is kind of a way of undoing the chain rule, is what it is. If I have a function, let's call it f of g of x, some composition, g prime x dx, what I can actually do to make this function or this integrand simpler is I can let some new variable u represent my inner function. So we'll typically let u equal g of x. It usually is some function that's inside of parentheses, some function that is under a square root, some function that is part of an exponent of an exponential function. It's an inner function. And the goal is that by taking the derivative or the differential on both sides, what I get is g prime x dx. And what I can do is this we said was going to be u, and this therefore would be du. So this entire integral just turns into f of u du, which looks simpler than what I started with. The reason you would need it is if you look at a problem like this, what function has a derivative of 5x times 5x squared plus 4 to the 8th? I don't know. If I wanted to go through and use the power rule, I'd have to distribute 5x squared plus 4 and multiply that binomial by itself 8 times in a row, or use some type of binomial expansion to do that, Pascal's triangle. I don't feel like doing that. Do you? And then still multiply by 5x in front. Oof, that sounds like a lot of work. So there's got to be an easier way, and there is. I see an inner function. I see a function inside of parentheses. It's a composition. So what I'm going to do is I'm going to let this 5x squared plus 4 inside my parentheses be my u. It's just a new dummy variable that we introduce. Now the problem is that because I've introduced u, I have to get rid of the rest of the x's in the problem. I cannot have multiple variables going inside of my single integral. So what I'm going to do is take du. So I'm going to take the differential of the left side and the differential of the right side. The derivative of the right-hand side would be 10x. Move my dx to the other side. Dx. Okay. So what I look at, what's left, this is my u, getting started, not bad. Now the problem is what's left is 5x dx. And what I see here is 10x dx. I want to try to make that look like 5x dx. That's what's left over. Let's see if I can change my highlighter color. That's what I want to be left. And so what I'm going to do is I'm going to make the 10 turn into a 5 by doing the legal algebra move on both sides. I'm going to divide both sides by 2. So I get 1/2 du equals 5x dx. Now I've got the blue piece that was left over inside of my integrand. So this turns into, and I'm going to deal with the bounds in a second. Let's leave the bounds. We'll talk about that in a minute. This is going to turn into u to the 8th times 5x dx, but we just said 5x dx is equal to 1/2 times du. So I'm going to highlight the pieces so you can see it. This is my blue piece. This is my yellow piece. And I can pull the 1/2 out front. It's a coefficient. So really, all I have is the integral of u to the 8th du. Looks a lot better than what I started with up here. This looks a lot more complicated. This line looks a lot easier to work with. And that's the whole point of making the substitution, is now we can take the antiderivative fairly easily. Now we still need to talk about our bounds. These were bounds in terms of x at the beginning. So it often helps if you put x equals next to those. We need bounds now in terms of u. And all we do to get the new bounds is we substitute in the original lower bound and upper bound into our expression for u. So if I evaluate here, my lower bound to start with was 0. So if I want to see what 0 outputs using this new substitution, I would just compute u of 0. 5 times 0 squared would be 0, plus 4 would be 4. So my new lower bound would be 4. And then I do the same thing with the upper bound. X was 1, So if I plug 1 into my U substitution, U of 1 would be 5 times 1 squared would be 5, plus 4 would be 9. So my new bounds become 4 to 9. That's important, especially those of you taking AP Calc. Multiple choice questions oftentimes will ask you to find not only the answer to a problem, but they might ask for an equivalent form of an original integral. Can guarantee you throw off answers are not going to change the bounds. You don't want to pick the answers that didn't change the bounds. You want the ones that have the new bounds substituted in for you. So make sure you're real careful about making sure you remember that step. Rest of the problem now just uses fundamental theorem of calculus. 1/2. I'm going to raise and divide, so the 8's going to turn into a 9. So I'm going to get u to the 9th over 9 if I use my reverse power rule. And I'm going to evaluate this from 4 to 9. So I'm going to get 1/2 times, you got 9 to the 9th over 9 minus 4 to the 9th over 9. So this would be 1/2. If I simplify this, this would be 9 to the 8th minus 4 to the 9 over 9. This is quite a big one. I don't even know if our calculator is going to compute this. This might work. Yeah, okay. So we get 1/2 times 9 to the 8th is 430, 467, 21, minus 4 to the 9th over 9. Two, 6, 1, 2, 6, 2, 4 over 9. Probably get a common denominator here, so I'm just going to use my calculator to do this one. That minus answer. Not the most clean answer, but if we multiply this by 9, this might be the best way to go. There we go. Minus 262, 144. There we go. 387. 1583, 45. Over 9, then we have a times 1/2 out front, so this will be over 18. That's an acceptable way to leave our answer. Most likely a problem you'll encounter will have much nicer powers to work with that are not so big, but that gives you the idea of making sure you can switch the bounds. Okay. You can also do this as an indefinite integral, so even if there's no bounds, you can use a U substitution. I would probably want to use it on something like this. I don't know a function that has a derivative of cotan. I know what the derivative of cotan is, but remember, this isn't asking for the derivative of cotan, it's asking for the anti-derivative. What function has a derivative of cotan x? That's what we're looking for. Now, it's not very obvious how to make a U substitution here. I don't really see an inner and outer function, so we're going to use a trig identity from the past. Throwback. Cotangent is equal to cosine of x over sine of x. So I'm actually going to rewrite this integral as cosine x over sine x dx. Now, at least now I have two pieces that I can work with. One of them is going to be my u. If you're not sure, try it out. Let's just say you're not sure and you want to let u equal sine of x. Du would be cosine x dx, which is good because that's what I see right here. Both of those are in the numerator. Problem is, if I was to do it the other way, let's say you thought maybe u should be cosine x, then du would be negative sine x dx. And the problem is my sine is in the denominator, but my dx is in the numerator. I need the sine x and the dx to both be multiplied together. And that doesn't happen in this case because the sine is in the bottom. So I don't want this one. This is what I want. I'm going to let u equal sine. in which case I get U on the bottom. This is my U right here. And my leftover part in green, I'm going to highlight this again. Let's do pink this time, see if this works. Cosine x dx, that's exactly equal to du. So I'm going to replace that with du. So I've got the integral of du over u, might help to write that as 1 over u times du. This is one that if you try to use the reverse power rule, you're going to end up dividing by 0. So you got to know this one is your natural log of the absolute value of u plus a constant. Again, a lot easier than having to integrate cotan directly. We've used this U-substitution that hopefully makes it a little bit more obvious that this is a lot easier to compute. Easier to compute. Please make sure the original problem started with the variable x, which means that when you're done with the problem, you have to put everything back in terms of x. Since u was equal to sine x, all I'm going to do is I'm going to replace u with sine x. Now I've got the problem back in terms of x. Now I'm done. Natural log sine x plus a constant. Absolute value of sine x. Okay. Hopefully that helps. I believe in you because you can do U substitutions. Okay, I'm done with cheesy math jokes. Happy mathing. Hope that helped.